I will attempt to solve European call option using Black Scholes equation. I'll go through every single details, so this might be a very long video. So this whole thing is inspired by Wikipedia. We start with Black Scholes equation. Where G, let me just finish the whole thing. Just to recall, it's R, it's interest rate. This is a time derivative, G. G is the function of maturity time and all the stocks. Mu is like just for notation, because I'm really comfortable with gradient and the Laplacian, this is defined as gradient of S with S direction, and Laplacian defined as derivative of S of the derivative of S. All right, so let's solve that. Just let's just the condition is on the right side. It's going to be all the thing in short, and on the left side I will go into all its glory details. That like left side and middle chalkboard will be all in its glory details. So we do a change of variable. For this, we do a C is call option price. Just a consistent, somewhat consistent with the derivation. Actually, it's not. Yeah, it is. And we will do a change of variable. C equals U exponential R plus. Sorry, I think it would be better to show the first change of variable. First change of variable is tau equals t minus t, where t, big T, is termination, the terminal, the expiration time, and Actually, it might be better to write it here as well. Change of variable. Tau equals t minus t, and then u equals c, which is the call option price, exponential negative RT. You can imagine the long, not T, tau. You can imagine as this essentially normalize the exponential growth, exponential decay of the value of the option, in the sense that the shorter the option is, the less valuable the time premium it has, because it's gonna go up. The less of, like, essentially, if you just let the money sit there collecting interest, it will be the R. So you try to do this change of variable to reduce the variation of to essentially let the effect of interest go away. So we plug those in to the equation, into the Black Scholes partial differential equation. We have negative RG negative RC, but it will become C. So for us, the C, it will be the G. C equals U exponential RT. I'll just double check, because I think they have a typo in Wikipedia. Yes, C equals UR tau, and DT equals D tau, because you don't really care about the constant, adding a constant behind it. So we plug everything into the partial differential equation. We'll have negative RU exponential R tau plus, do the derivative of tau U exponential R tau and plus mu S another change of variable is x equals ln S over K. We will know ds equals ds. You can write it as, you can write derivative of ds equals dx multiply x on both sides since x is ln s over k, then we'll have let us write everything in details. Ln s over k, and I think it should be very trivial for most of y'all. This thing equals 1 over k. So do the derivative whatever inside, and then s over k. Do this as a whole thing. Like so, ln x is 1 over x. Then this ended up become the k cancels out 1 over s dx. Similarly, through this derivation, we know no space. Okay, similarly, ds squared, so the Laplacian equals 1 over s squared. So you just done it twice of this type of thing. Actually, as I promised, I'm gonna write everything in this details. Let me just actually write that as well. Similarly, ds equals ds s 1 over and then you have negative s squared over you have s over 1 dx s over 1 dx equals s squared Okay, let's then plug everything in. We'll have negative RU exponential R tau plus U R tau plus mu s 1 over s dx u e r tau plus half sigma square s square 1 over x square, because this is you plug Laplacian back in, it's this. 0. So something amazing happened. Let's just expand this. D tau u e to the r tau. Remember, u is a function of tau. Then you imagine those are become two functions. So du tau, you have e r tau d tau u plus u multiplied by the derivative of e r tau will be r e r tau. And something great will happen very soon. U e r tau. Remember, we just derived this plus e r tau d tau u plus u r e r tau. You saw those two cancels out, which is really good. Since those are the derivative to x, where u is a function of x, whereas the e r tau is not a function of x. So you can take it straight out. And you can see, lovely, x is, as it cancels out here and here. You will get mu read as x u plus half sigma square gradient of x u to the Laplacian of u equal to 0. So we clean everything up, multiply both sides with e to the negative ru, just essentially cancels out all the ru's. That's our r taus. And then those two terms cancels out. We have something quite pretty. Now I'm second guessing of what I had here is correct. So what we have here, derivative of x, maybe there's a sign issue that I need to address. So I don't know if I did this part correct. So we'll put a question mark on this. I might have done this wrong. Nonetheless, we're really close to the greatness. Set mu to 0, because at least in my intuition, we can absorb the mu. Not necessary. You can it still have different action, but for no drifting, for a thing that has no drift, where mu is 0, we have, so this term is 0. We ended up. So I think if I don't know if there's anything with sinus wrong. anyway, we have equals, there's a sign mistake. Somewhere. 1/2 sigma square. I really wanted to have Laplacian. This is every physicist well-loved diffusion equation, or a fixed one. So diffusion equation, we'll make a bold guess what it is. U equals sigma square root 2 pi tau integrate from negative infinity to infinity u naught y exponential negative x minus y square over, just double check I'm not making any too much mistakes, 2 sigma square tau dy. So if you check my my diffusion equation fixed laws video on physics, you imagine essentially as a Gaussian distribution relaxes over time, while it is try to calculate the coefficient of an initial condition of an initial distribution of a Gaussian distribution with the initial condition. It's very commonly used in quantum mechanics, but anyway, I mean, I don't know my audience physicists. I think you have similar application in mathematics as well. Anyway, but this is a solution. We made a bold guess. It is just the Gaussian distribution with a linear relaxation is a solution. So it's very common for us to do a plug and check, just check if it works. So just this is a guess, right? We need to prove this guess is correct. So let's just calculate the derivative of t, the tau u t equals sigma square root 2 pi tau. You can imagine, just put you have tau in two places. One is here, another is here. So we'll first do the derivative of here, like in the front. We will have essentially negative half and tau to the 2/3. That's pretty trivial, I guess. It's just normal derivative. And with all that jazz, let's just denote this whole thing as, I don't know, let's see, f maybe? F xy tau. And we need to do the derivative of here. We have sigma square root 2 pi tau integrated from negative infinity to infinity. There is one thing to recall. I guess we can add our trophy here, mu equal to 0. We have a beautiful diffusion equation. And we'll try to solve it, of course. We made a guess, and also it's good to know from here to here, derivative of x from negative infinity to infinity f xy dy. This is for general f, general function. You can do negative x fx to take the derivative in because it's not integrated through x, and this is nothing, no function here on with respect to x here. F dy. Hopefully you can see it. Anyway, this thing is called, let me see what it's called. Leibniz rule. We have this, we can put this in, put this whole thing in, and essentially you just, since it's an exponential, you just do the derivative inside of here, and the exponential doesn't change, so you have a nice intact f with a derivative of this inside exponent. By inspection, it's very simple, just 1 over t, right? Sorry, 1 over tau, which is square. So when it's 1 over tau is negative 1 over 2, negative 1 over 2 tau square. And those negative sign cancels out. And voila. You get this. This is d tau. And we're going to do a Laplacian of u. I'm going to take us some effort. Since there's nothing, all of the stuff is, all of the x is just here. You just need to do that twice, which is not too difficult. This thing doesn't change. You just need to do the derivative, the double derivative of this thing, right? You have u naught y, that thing doesn't change. You do a derivative of x of derivative of x of that. It's probably better to use that instead. There instead. This is gonna be messy real quick. square you wouldn't be able to see. So exponential negative x minus y square over 2 sigma square tau dt dy. So let's just do this bit, shall we? Negative x minus y square over 2 sigma square tau. That thing equals, let's do it first, derivative. The exponential never changes, never been bothered. We'll have negative 2x minus y 2 sigma square tau exponential yada yada, right? You just essentially do the derivative of this. It's basically x squared, 2x, and then we 2 cancels out. Then we'll do it again. We do the derivative of this thing. Actually, it's better to do it like that. All right. Do the derivative of this left bit. This is 1, so it's negative 1. This is going to be 0 because y is not a function of x. So then it will become sigma squared tau. The exponential is intact, I will write it later. And you do the derivative of this again, which is exactly the same thing. Then you have x minus y squared sigma to the 4th tau squared. Let's sanity check of the unit, which is a physicist's favorite tool. You check the unit is good. Which it is. Wait, is it correct? Something to check. What I'm checking is just a unit, essentially. You know, whatever's inside the exponent is a unit of 1. Meaning, in this here, for physicists, the bracket sometimes you can just use it as like the unit of this is 1. It's a constant. So essentially, the unit of x over y equals unit of sigma squared tau. And then I use this to check if the unit is correct. And this can be reduced, essentially, this can be reduced as, since this over sigma squared tau is unit of 1, then this can be reduced as unit of unit sigma squared tau, which is unit matching, which is great. We're in good shape. And let's just write the exponent celebratorily in full. It's pain to write the whole thing. There we go. So now we have d tau and the Laplacian. And then we'll plug everything in. How should we plug it in a nice way? All right. uniform everything with a single step, or maybe with not a single step. I promise to be not skipping steps. Okay, let's not skip steps. D tau du is, you can write, I'm gonna skip a few steps, I'm sorry, this is too tempting. It's a constant. You have negative infinity to infinity. And f x y tau. So just imagine it's here, this is here, and what we left on this first term, what left is negative 1/2 tau, because 1 square root tau goes to here, and then we're left with the 1/tau here, which is this. And then second term, we have this, we have f, we have this block, which is x minus y square over 2 sigma square tau square. And then we have 1/1 sigma square, sorry, 1/2 sigma square, and multiplied by the Laplacian. Because remember, this whole thing is fx. And we ended up find out this and this is fx, right? Sorry, this whole thing is f. And we find out, of course, exponential is always intact. Then we're left with this thing with fx. So we just need to plug this into here, which 1/, it should be, oh, I should have said, I should have said du minus 1/2 sigma square Laplacian u equals to this. Equals to this, star equals to this. So we just try to check this minus this equal to 0. If it's equal to 0, this is that Gaussian is a solution. So sigma, let's get back to it, 1/2 sigma square multiplied by this thing, 1 minus, so it should be minus, because here, sigma square tau plus x minus y square over sigma 4 tau square. And then close bracket dy. And the star, I'll just write the whole thing out. D sigma u plus minus 1/2 sigma square Laplacian u equals, I'll write it smaller, sigma 2 pi tau, negative infinity to infinity, f x y tau. Let's just write everything celebratorily, because we already see what is about to go down. This cancel this out, plus 1 or 2 tau. This cancels become positive, this is to become negative. X squared, sigma to the 2, sigma to the 4, sigma squared, tau squared. How lovely. We have this cancels out, well, these plus half, I forgot half here, half to here, half here. These two cancels out. We have 0, which means the Gaussian is a solution. This is a solution. That is noteworthy, so I put it here as U x tau equals sigma over 1 over sigma square root 2 pi tau integrated from negative infinity to infinity is u naught y exponential negative x minus y square 2 sigma square tau dy. And that's a solution, one of the solutions to a diffusion equation. So what about it? How can I use it to price a stock? The only thing we need to do is to apply the boundary condition. Whereas, essentially figure out what u naught y is, what u naught is. For us, we are doing a European call option where u naught is k exponential x plus minus 1, where x plus, or we're going to say, I think for the clarity, we should say maximum of x or 0 minus 1. Essentially, as a compact way to say it, essentially we can write it openly as, we write it in a little bit more straightforward way as k equals exponential of x minus 1 when x is greater than 0, and it is equal to 0 when x is less or equal to 0. When it's less or equal to 0, this is 0, e to the 0 is 1, 1 minus 1 is 0, and this is 0. So, and recall x equal to ln s over k, then what is e to the x? Then we have 0 k s over k minus 1. I wish I have a longer chalkboard. Let's just simplify it. K multiplied by 1 s over k is s minus. Let me rewrite it in the smaller font, because this is really nice to see in one line. So we have k e to the x minus 1, 0, when x is greater than 0, when x is less or equal to 0. and we can, since we know x equal to ln s over k, we will have k e to the ln sk is 1s over k minus 1, and is 0 when ln s over k is less or greater than 0, or ln. If we take ln, this on both, take exponential on both sides, it still holds because it's monotonically increasing the exponential function. Then we have s over k less or equal to exponential of 0, which is 1. What I'm getting at, this can be written as oh, come on, not enough space, s minus k 0 when s is greater than k, and it's 0 when s is less or equal to k. This is at the time, at the expiration time, the payoff is the stock price minus strike price. And if it's, which is in the case of in the money, it's s minus k. And when it's out of the money, it is 0. And that's a boundary condition, which is rather intuitive, right? Like as a u, because u is just u is similar to c, which is just adding an exponential, and that for exponential here, it's just 0, because it's just 0, then it's 1. It's 0, tau equals 0, and then the exponential of 0 is 1. Then we have, for different s, is our beloved payoff function, just written into a form of a change of variable. So since our chalkboard space is very precious, I will erase that big square. We know it is proven now. It is a good solution. The Gaussian is a good solution. So let's just plug in this function. We have u equals negative infinity to infinity with sigma square root 2 pi tau with k exponential max x of 0 minus 1 and exponential minus x y equals 2 sigma squared tau dy. Since this whole term turns to 0 when x is less or equal to 0 for this, we can truncate integration now. Just going from 0 to infinity, then we don't have this condition of max of x to 0, because anything less than x, sorry, this is not correct. This is very confusing. Sorry, this is a function of y. As it will be really good to be consistent, I guess, so that it doesn't confuse any readers. Yes, there we go. Beautiful. Essentially you can truncate that from negative infinity to 0, from 0 to infinity. Then we don't have this annoying condition like a max y and 0. Then we have sigma square root 2 pi tau k of exponential y minus 1 exponential let's just skip a step since we won't have so little of a precious chalkboard. K is a constant, so we can put this in. So from 0 to infinity of exponential of negative x minus y squared 2 sigma squared tau minus plus y minus exponential x minus y squared over 2 sigma squared tau dy. And the goal is to create, since this is a Gaussian, we can make it a shorthand notation to make it look nice and pretty. So those, all of them are quadratic equations, like those inside of the exponent, and we'll make it look nice and pretty by doing this. Since this is already done, we don't necessarily need to worry about this one. Anyway, but this one needs some work. So we have this thing equals negative y squared, so let's just sigma tau, negative y squared plus 2xy minus x squared minus, plus y 2 sigma squared tau y equals since we are trying to combine them as in the form of alpha y squared plus beta y plus gamma in this form, so we gather y squared, something with first order and zeroth order. So we have negative 2 sigma squared tau y minus, since this is minus here, just for convenience, let's just do this. Minus, take it all the way out, so every single one changes sign. Right? Because we'll take the negative sign out. Then we have these, which is conveniently both are negative sign, and it has both a 2 in it. So we have x plus sigma squared tau. Wait a minute. Did I make another mistake? Oh wow, surprisingly no, I didn't. And then this whole thing square, and then whatever square need to compensate this. So we have, so by squaring this for the, since we have this one, and we need to find this one to compensate this. So this square is x squared, so this already exists, so we need to minus 2x sigma squared tau minus sigma 4 tau squared. Voila. Nothing too disgusting. So we need to just go for change of variable to change to make everything. I mean, I'm not skipping steps, but I think I may erase those to keep this this font size legible. So I have k sigma 2 pi tau, and then the first one is, keep in mind it's still with this from 0 to infinity is still with respect to y. Then we need to create, I guess I just need to not skip any single steps so that it will be less confusing. Exponential of y minus x plus sigma squared tau square 2 sigma squared tau, and then e exponential, and this bit is just a constant with respect to y, negative, oh apologies, there's a negative sign here, since there's a negative sign here, so this negative will become positive. We have sigma squared tau here when they become x, and then become plus half sigma squared tau. And to make it look like more defined, there's no negatives up there. So we need this whole thing, this whole exponent square rooted, and with that you ended up with need an additional constant to compensate for that, which is square root 2 sigma squared tau, and then the dy, the new d, which is huge, y minus, gosh, I don't have space. Square root 2, I want to make the point, tau, okay, x plus sigma squared tau, I guess good enough. So this is the square root of this, whatever inside of this bracket. And then we deal with the second term. Second term here is much more welcoming, at least shorter. is a minus, because it's minus here. Less confusion, I should just add giant right here. We have similar drill, exponential. Oh, apologies. I do not want the square root here, because we want to keep it like this. Actually, no, I have space. Wow, I write it OL now. Square root, square T, tau, d, y minus x square root sigma square tau. There we go. Beautiful. And some other things. Negative y minus x squared over 2. 2 should be there, sigma squared tau. Then we have square root d y minus x sigma squared tau. That is it. You have a square root here. You have two pretty decent looking Gaussian. And we run out of chalkboard. Let me use a left chalkboard. Let me just erase the change of variable to derive to the diffusion equation. Let's just use this bit. So recall this whole chalkboard is just to derive to the diffusion equation. Anyway, hopefully the phone hasn't died. I will be very sad if it does. And hopefully this one board is enough. All right. We can do a change of variable again. Z1 equals y minus x plus sigma squared tau over square root sigma squared tau. Z2 equals x, so y minus x square root sigma squared tau. And we have something a little bit more pretty. Keep in mind, we are changing to z, and this no longer is integrated from 0 to infinity because we need to put that in. Put 0 in y here, then we have sigma over what will happen. Can I fit everything in one line after changing to z? We'll see. Integrating, not from 0 to infinity, but from there to infinity, which is negative, oh sorry, here, negative x plus sigma square tau over square root sigma square tau, infinity, exponential, I don't think I could do that. X plus 1/2 too long. Z1 square equal dz1. I guess I need two lines. Minus 1 over sigma square root 2 pi tau. And this integrating from negative x over square root sigma squared tau. Yes, that is correct, to infinity. And this doesn't have anything in it, which is this. And I also forgot everything have sigma square root tau, sigma square root tau. I really like this part because it's really getting easier and easier. And just by inspection, tau cancels out, sigma cancels out, and you're left with two beautiful, simple two simple Gaussian. By definition, n, let's give it a n alpha is 1 over square root 2 pi from negative infinity to alpha of exponential of z squared over 2 dz. And almost by symmetry is equals 1 over square root 2 pi alpha plus e to the z squared negative, of course, 2 dz. This is very intuitive to think about, right? You have a Gaussian, nice Gaussian. Right, this is negative alpha, or just for simplicity. By symmetry, those two areas, this is this area, this is this area. And those two areas are equal because it's by symmetry. We have similar things, right? We have this. Then this can be written as, I forgot a k, isn't it? Yes, I did. We're left with k, and this is 1 over square root 2 pi, and this is exponential x plus, this is a constant with respect to z, and this 1 over square root pi, this thing is just the definition of n, the accumulated distribution integral, and it becomes n. You change the sign because it going from, yeah, so this is more like negative. It's a definition of this is like that, and then for us this is this. So you need to flip the sign right here, which is x sigma square root tau plus sigma square tau, and minus k n x over sigma square root tau. Would you look at that, finishing one more. So this is the call option price. If I am correct, I will be very happy. And hallelujah, I am correct. And just write U x tau equals k exponential. I guess just to match with what textbook have, I'm gonna erase this. I guess I have to. Okay, then we just need to make it look nicer. D plus minus equals sigma square root tau x minus plus 1 over sigma square tau plus minus half sigma square root tau. And this can be written as k exponential x plus 1/2 sigma square tau and d plus, yes, plus minus k and d minus. Also, sometimes people like d plus equals d1 and d minus equals d2 or some other convention. And yeah, that's a solution. But I'm not necessarily satisfied with it, because the x is long S over K. And I want to make it look exactly with all the nitty-gritty we have. I guess we could, it doesn't hurt. C equal U exponential R tau, is it? Yeah, right there in the top right chalkboard. So we have C equals, you have the interest, you have the K, which is the constant. And there's some magical way you have to get, yes, of course, X is here. I can find X somewhere. K exponential half sigma squared tau and K over S over K. Because exponential X is S over K. you know what? I'm writing in the wrong direction. I should write this k s over k, an exponential 1/2 sigma squared tau, and d plus minus k and d minus. And of course, k cancels out. We have c equals exponential r tau s exponential 1/2 sigma squared tau and d plus minus k and d minus. I think this is more intuitive because I want s to be there somewhere. And this is the expression of tau and t, which is good enough for me. I guess I will just write everything as c s k tau equals exponential r tau s exponential half sigma squared tau and d plus minus k and d minus, where d plus minus equals sigma square root tau. Oh, okay, let's just substitute that as well. Substitute that x as well. Ln s over k plus half sigma squared tau plus minus half sigma squared tau. And, oh, need to close that. And that's the solution. Somehow this may take very long. European co-options using Black Scholes equation will ended up. So let's recap. What goes from the Black Scholes partial differential equation, and we use change of variable, change tau to t minus y, u is like make it not worry about the interest, like interest, and then have x equal to ln of s over k to just eliminate the s, and make it looks pretty. At least for me, it looks very pretty. It is a differential. It's a diffusion equation if you assume the mu equal to 0. And then that solution, as we tested, somewhere there, right here actually, is 0. It all cancels out. We got the solution of that diffusion equation can be the linearly relaxed Gauss normal distribution. And we add, and then this is essentially the general solution to a degree, general solution of the diffusion equation. And we supply the boundary condition, which is pretty much the payoff function at the terminal at the expiration time, which is the tau equal to 0. And it's very intuitive. U naught equals S minus K, which is the stock price minus strike price when you're in the money, where stock price greater than strike price, and you got nothing when you're out of the money, which is strike price lower equal to the strike price. We ended up solving this equation by pretty much make this whole thing looks nice enough into a quadratic equation and make it look like a two term as a Gaussian distribution. And then we do a cumulative Gaussian distribution to then right there, and I will substitute back the change of variable, the u and x, and I ended up getting this, the call option pricing in European call option. You can imagine, I think I'm not an authority of trying to find intuitive understanding, but here's a attempt. This interest rate, and S is the stock price. At any given time, the stock price, you have some type of premium of the risk, like how, if the more varied it is, the sigma is pretty much, you know, based on the definition of like S equals, when you derive the Black Scholes equation, you have something like that. And this is like how much it varies as a Brownian motion. And you have the more valuable option become more valuable when it's more volatile, which makes sense. You have more money to earn, I guess. To a degree, you have more money to earn. And the Gaussian distribution is when you're having what is that? Oh, stock price over strike price. Or strike price and exponential. So as you're in the just integrate all over here. And minus the probability of stock price or strike price. Anyway, I think after next week's class, I will be able to understand better of the solution. But here is the take-home message. This is the one. Quick recap, just second time recap, I will be much faster. Black Scholes equation, change of variable to give us, and assume mu equal to 0, give us diffusion equation. And the Gaussian function is a solution to diffusion equation, at least in this form. And we apply boundary condition of the European call option, ended up getting this nice expression. And that's the full derivation.